Right, good day, ladies and gentlemen. So we continue with chapter 4. This is the third part, which is to be put online and will be discussed or taken for questions and answers on Monday, 11 March. Right, so we're going to look at arithmetic operations today, and the arithmetic operations involve adding, subtracting, multiplying, and dividing. You know, the same basic arithmetic operations that you used to in math. Now we can apply these operations to integers and floating point numbers, which basically is the same as real numbers. But in this course, we're really just mainly going to focus on integers. Right, so arithmetic operations on integers. We're first going to look at that, well, as I said, we're only focusing on that. So all arithmetic operations such as addition, subtraction, multiplication, and division can be applied to integers. Now, it can also in the real world be applied to real numbers, but we're not going to do that. Now, although multiplication of integers can be implemented using repeated addition, the procedure is not efficient. We can say the same for division. Although division of integers can be implemented using repeated subtraction, again, that's also not efficient. Let me just give you an example. So if we multiply the number 2 by 5, then we basically can just add the number 2 5 times together. So it's 2 plus 2 plus 2 plus 2 plus 2. And that's basically that simulates the multiplication. You know, it's repeated addition. Same for division, it's repeated subtraction. But as we say, it's not efficient. There are better ways. One of the efficient ways to do it is by using Booth procedures, but that's beyond the scope of this course. We're not going to do it in this course. And for this reason, we only discuss addition and subtraction of integers in this course. Right, so just to bring you up to speed again, we know how to do simple addition. Now we should remember that when we add integers, we can do it column by column, just as we are able to add simple integers. So the following table shows the sum and the carry. So basically what it says there is that if we have two zeros, you know, if we add 0 to 0, we get 0. So the actual sum is 0. And there's going to be no carry. When we have 1, 1, then basically the sum is 1. You know, 0 plus 1 is 1. When we have two ones, then the sum is actually 2. But we know we can't have a 2 in binary. We can only have a 0 or a 1. That means we will have to have a carry of 1. And when there are 3 ones, then basically the sum is 1 and the carry is 1. Let me just quickly show to you what we mean with this. You know, so if we basically have to add 0 and 0, the result of that's going to be 0. All right. So in fact, we can indicate that by 0, 0. You know, if we add all of that, we get 0, 0. It's just simply just 0. Okay. If we have the following, for example, if we have 0, 1, and we add 0 to that, then basically if we do simple calculation, 1 plus 0 gives us 1, and 0 plus 0 gives us 0. So the answer is 0, 1, which is the same as basically just saying 1. All right. If we have the following, 0, 1 plus 0, 1, we have to do that calculation. Then we say 1 plus 1, and this is the case of the two zeros that we're talking about there. So 1 plus 1 gives us 2. But we know we cannot have a 2 in binary, So it resets. In other words, the value is 0 and carry 1. So if we carry the 1 over, then we have basically 1 plus 0, which gives us 1. All right, and that's basically in binary. If you have binary 1 plus 1, then we basically know in binary the answer is 1, 0. Okay. And now if we have 3 ones, so for example, my space is running out, I'm going to try and do it here. So if we have, for example, 1, 1 plus 0, 1. So now in actual fact, that's the binary value 3, that's the binary value 1, and if we have to add all of that, then we say 1 plus 1 gives us 2, but we know it's a carry, so 0, carry 1. 1 plus 1 plus 0 gives us 2 again, so again the answer is 0, and the carry of 1, which basically means the answer is 1, 0, 0. So in other words, we know 3 plus 1 gives us 4, and this is in actual fact the result for binary 4. All right. So that's basically the basics of it. So if we have 5 plus 4, if we convert 5 here and 4 to binary, we know that's the binary representation. 101 for 5 and 100 for 4. We assume using 4 bits. And so if we do this calculation, in other words, if we add this, 1 plus 0 gives us 1, no carry. 0 plus 0 gives us 0. 1 plus 1 gives us 0 and 1 carry, and then 1 plus 0 gives us 1, so the result is 1001 in binary. So, and if we convert 1001 back to decimal, we'll basically see that 1001 is 9. Okay. Knowing that, let's try and do this on 2's complement integers now. So when the previous slide had to do only with addition, all right, but when we encounter subtraction, the subtraction operation in the computer actually simply changes it to the addition operation. So what does this tell us? In actual fact, with this trick that we're going to see now, computers actually don't really do subtraction. They do a trick and then they do addition. And that trick basically is to make 2's complement of the second number. So what we're basically saying, if we add the first number or the second number, we just do it usually with add. But now, in this case, we are subtracting. So if this is the case, then with this trick that we're doing by saying A minus B, you can actually say A plus, so we change it to a plus action, and we do this strange thing here, which really isn't so strange, which all just means is we change the value B into the 2's complement of B. And you'll remember correctly from chapter 3, doing a 2's complement, we can use 2 approaches. We can start copying from the right until we get a 1, and then we stop, and then we just do a 1's complement to the left. Or we can do the approach given here, which basically says get the 1's complement. This basically here means the 1's complement of B, and simply add 1 to that. That's the other alternative to doing 2's complement. It's a 1's complement by adding 1. So in this trick that we've just done here, we have changed this subtraction operation to this addition operation. And now that means less things have to be done by the processor. It knows literally only just how to do addition with this trick of 2's complement. Yeah, so let's do some examples for you to see how this works with 2's complement integers. So just take note, we are going to use 2 complement integers now, and assuming It's 4-bit binary. Right. So let's just look at some normal subtraction. We all know that 5 minus 3 gives us 2. And if we just convert that into binary, it's 0101 minus 0011. That will give us 0010. So that the 10 there is 2. Okay, so nothing new there. That's the normal mathematical way of doing the subtraction there. But now, how it will be really done by the processor in the background is that we know that the processor can really only do addition, not subtraction. So with this trick, as we said on the previous slide, the subtraction here is now changed into addition of the 2's complement of b, and we now know from the previous slide the 2's complement of b is simply the 1's complement of b plus 1, or in mathematical way described as the 1's complement of b plus 1. So a stays the same all the time, so here is basically a and b, so a subtracted to b we know now changes to an addition. And sorry about this, that line should have appeared above here to indicate that that's the 1's complement of that number, which is basically then, if we do the 1's complement of that number, it means it's flipping the bits. So 0011 becomes 1100. And once we have that, we simply add 1. So we just quickly do the addition of that over here. We basically say 0 plus 1 gives us 1, and the rest remains the same, 0, 1, 1. So we have 1101 as a result there. So remember here, over there, here and here, a is just the value of a, and we just wrote this value of b over here. We just wrote down there. Sorry, this should be a 1, so it's 1101. Okay, exactly as it is here, 1101. And then we simply do an addition of this value with that value. So bit by bit from the right we start. 1 plus 1 gives us 2, but we know that resets to 0, carry 1. 1 plus 0 gives us 1. Then we have again 1 plus 1 gives us 0 with a carry of 1. And 1 plus 0 plus 1 gives us again 0 with a carry of 1 over there, which comes and lies over here. But now you'll see that is a 5th bit. We are only working with a 4-bit value here now. So again, like in this trick of 2's complementing, if it falls off on the left, it simply falls off. So that 1 is ignored. And what remains here? 0, 0, 1, 0. And 0, 0, 1, 0 is exactly equal to that originally, 0, 0, 1, 0. So can you see with this trick of doing, instead of a minus b, we can say a plus 2's complement of b gives us the same result. And what we've done now is that typically your processor only have to have one function built into it in its circuitry, and that's addition. It didn't really do subtraction here. It did addition with a trick of making something 2's complement. Here's the same example, but just doing 8-bit binary. So you can see it will still work. Doesn't matter if it's 4-bit or 8-bit or 16-bit or 64-bit, it will always work. So here we now just use 8 bits, but you can see it's still binary 5, and here binary 3 will still give you that result. And to prove it, we're going to do this again. So here is A, and there's B. It is subtraction, but now we do the trick of changing it to the addition of the 1's complement, as you can see here, plus 1, the 1's complement of B. And so if we do the 1's complement of b, we're flipping bits, so this entire value just becomes that, 1, 1, 1, 1, 1, 1, 0, 0, plus 1. So if you simply just add the 1 there, then basically the result of this you can see is that value over there. So that is B, and this is still A. And we now we just wrote it underneath each other to do easy addition arithmetic here. So we say 1 plus 1 gives us 0, carry 1. 1 plus 0 gives us 1. 1 plus 1 gives us 0, carry 1. 1 plus 0 plus 1 gives us 0, carry 1. And so we go on. And gives us 0, carry 1. And gives us 0, carry 1. 0, carry 1. 0, carry 1. And then we're done. And there's the last value. But again, this is now a 9th bit. We are working with 8-bit binary. So in other words, this bit simply falls off. We can ignore it. And if you look at this value over here, it's still 2, or binary 2, still the same value as we had there with this trick. Nice trick, hey? Let's look at more examples. So here's just the generic flow chart to show you how it should be done. So we basically have R, or result, and we're going to do either A plus B or A minus B. Right. So we start over there and we look what we have, and we say if it's addition, we simply skip to the next step here and simply do normal integer addition bitwise A plus B, no problem. But if it was subtraction, if it was negative, we first have to do the 2's complement of B, which means 1's complement of B plus 1, and then we do the simple addition again of A plus B. Right, so that's the general procedure. Yes, just another way of stating it in words. So adding 2 integers in 2's complement. So A is the left number, B is the right number. So you add the right number to the left number, or vice versa. So step 1, if we are subtracting, then first set B to the 2's complement of B. Right? And then we do normal addition between A and B, bit by bit, from right to left, as in the examples I've shown you. Let's look at more examples. So here we have 2 integers A and B. Again, that's stored in 2's complement format. So take note of that requirement there. Show how B is added to A. So there's the key word. We do addition, and we know it's in 2's complement format. So we know A, in this case here, is in 2's complement format, and B is in 2's complement format. If we look at these two values, we can immediately see that A is positive because it starts with a 0. B is also positive because it starts with a 0. So no problem. If we go now and simply convert that value here and this value over there, we will see that that value gives us 17, and this value over here gives us 22. So what we in actual fact, if we look at our formula says, what do? We do addition. So then we simply take whatever is in A and whatever is in B, and we add them. So there is A, just written over there. There's B, written over there. And we do simple addition. So 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. So far no carries. 0 plus 0 is 0. Here's going to be the first carry. 1 plus 1 results in a carry. And then 0 there. There's the carry of 1. 1 plus 0 gives us 1. And the rest just remains 0. So there, the result that we get over there, if we convert this value, which basically means everything there, from binary to decimal, 100111 gives us 39. I'm not going to do it now. You can go and for some revision do it yourself, but you will see that 100111 gives us 39, and that's the right result. A plus B, which is 17 plus 22 is 39. Now note, we explicitly put the positive signs there because we're going to do some other examples now to show you the difference between them. Okay, so now let's look at the next example. This example says B is added to A. This is A, this is B. Remember, they are stored in 2's complement format. If you see, you can immediately see with the 0 there, A is a positive number, but hold on, B is a negative number. Yet we need to do addition. That's fine. So in other words, if we write this down as in the previous way, if we convert this number over here, this number of A, if we convert that to its decimal equivalent, we will see it's 24. Because it's a positive number. This one here is negative. Let's just quickly do it ourselves to see if that value really gives minus 17. So we know that 1 is the, it indicates that it's minus. So what should we do? To convert it to a decimal value, we do a 2's complement operation on this. Alright, so let's do the other method now. To say we start copying until we get a 1 from the right. So we get a 1 over there. So we've handled that first one. And then we stop copying. The rest of them, we do a 1's complement, we flip bits. So that next one becomes a 0, a 0, a 0, 1, 0, 0, 0. And if we now convert this value to decimal, we get 1 plus 16, which gives us, in actual fact, 17. And because it was negative, we know it's minus 17. So this is an example where we're still doing addition, though. All right. We are just adding a negative number. Think of it in that way. So in other words, it's 24 plus the negative number 17, but it's plus or addition. So what does it mean? Because this is in 2's complement, we simply take the two values A and B and add them bit by bit. Because it was addition. Alright, so no other conversion necessary. We take the positive number A, we take the negative number B, and we add them bit by bit. Because the operation was addition. So we do that bit by bit. 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0, carry 1. 1 plus 1 plus 0 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. And this last carry here simply falls away because we are only using, to count there, 8 bits. Right. So in other words, if we now look at this value here, and we convert this to binary 0, 0, 0, 0, 0, 1, 1, 1, we get the value 7. And that's in actual fact correct. The positive number 7 is the answer. So 24 add negative 17 gives us 7. If you do that, the logical mathematical calculation. Now the question is, what if we do this? What if we change this positive to a negative and this negative here to a positive? So in other words, like in the next example, we're basically saying we subtract this positive number. So now the operation is subtraction. So now we know we have to do something in addition here. All right. So what was the original numbers here? A, 24, as you can see there. So this is A, represented it as a positive 24 because it starts with a 0. So you can see normal binary positive 24. And we also saw that 17 was positive. So this is the positive representation of 17. All right, positive 17. But now we need to do subtraction. So when we need to do subtraction, we know A stay as it is. But B, we first have to go this thing over here. We first have to go and convert or do a 2's complement on there. So let's do 2's complement on this B value quickly. So we start from the right and we copy until we get 1. It is a 1. So the next of them we simply flip it as a 1's complement. So that becomes 1, 1, 1, 0, 1, 1, 1. Alright, so this value there is basically what you see over here now. And now we simply do an addition operation between A and the new B. Excuse me. So if we say 0 plus 1 gives us 1, 0 plus 1 gives us 1, 0 plus 1 gives us 1, 1 plus 1 gives us 0, carry 1, that gives us 0, carry 1, 1, 0, 1 gives us 0, carry 1, gives us 0, carry 1, gives us 0, carry 1. This carry falls away, and what we're sitting with is this result here, which is 7. In other words, the answer is still 7 if we do it this way around. Let's just do some more examples. In this example here, we say, again, do subtraction. So here's A, there's B, and do subtraction again. So because we need to subtract, we will know we will have to do something extra. Right? A is this value over here, B is this value, but B is negative. Right? So B is negative there. So in actual fact, what we're saying here is positive 24 subtract negative 27. Now mathematically, if you do this calculation, 24 minus 17, we know the minus and minus results in a positive. So it's actually 24 plus 17, which will give us positive 41. That's the logical calculation. But how to do it in binary now? We just follow the procedure. We know A stays as it was over there. Nothing changes. But we realize that the operation is subtraction. That means B, we first have to do a 2's complement. So we start from the right. We copy until we get a 1. There it is. The rest is basically then 1's complement like that over there. And so this value over here is what we're then going to use as B, as you can see it over there. And then we just do the normal addition. So 0 plus 1 gives us 1, 0, 0 gives us 0, 0 plus 0 gives us 0, 1 plus 0 plus 1 gives us 1, 1 plus 1, 0, carry 1, 1 plus 0 gives us 1, 0, 0. Alright, so and the actual result in the end is that over there. If you go and calculate 101, 001 from binary to decimal, you'll actually see that that is the result of positive 41. Alright, so let's look at the next example. Now we change the example. We again see there's subtraction. A is now a negative number, as you can see. So if we do the conversion of A from this 2's complement format that it is stored in, you'll see it's minus 35. We need to do subtraction over there, and we need to add or subtract the positive number, this. So in other words, it's still subtraction. We will have to do something extra. In other words, we still have to change this value to its 2's complement. That's the rule. We start copying from the right until we get a 1. So we get 0, 0, 1. From there we do 1's complement, 1, 0, 1, 1, 1. And this is the value that you see over there, the new B value. We simply take A and we add this A and B bit by bit. 1 plus 0 gives us 1, 0, 0 gives us 0, 1 plus 1 gives us 0, carry 1, then 1 plus 1 plus 1, gives us 1 carry 1. 1 plus 1 plus 0 gives us 0 carry 1. 1 plus 0 plus 1 gives us 0 carry 1. 1 plus 1 plus 1 gives us 1 carry 1. 1 plus 1 plus 1 gives us 1 carry 1, and the carry there you can simply ignore eventually. This is the value we are interested in. Hold on. Remember, this is stored in 2's complement. So this 11001001 basically means minus 55. And to get to the minus 55, we first have to do a 2's complement on this result to check if it's really minus 55. How do we do that? Start at the right, copy until we get a 1. We've got that. Now flip bits. 1, 1, 0, 1, 1, 0, 0. And now if we do the calculation here, 1 plus 2 plus 4 plus 16 plus 32, if you do that calculation, is nothing else than 55. And we know it was a negative number, so it must have the negative in front of it. All right. So you see this works in all possible ways to do this subtraction or addition, as long as these numbers are in 2's complement. Hopefully now you start to realize and grasp why are we teaching all this 1's complement and 2's complement and masks and whatnot, because we're starting to use these all of these together now to really start showing you how the calculation is really working inside the CPU. Yet another example. I think this is the last example. So here we have two integers a and b. We need to add them, right? So the first integer here is a. It's a positive number. So if we convert this value to a positive number, you can go and do it yourself, we will get 127. And this is also a positive number, as you can see over there, and this is a very small number, the number 3, if you go and convert that. So 127 needs to be added to 3, or other way around, 3 needs to be added to 127. So logically we know that result is supposed to give us 130. Now if we follow this process, let's see what happens. So the addition is add, so nothing special has to happen with b. We simply take a and b, so there's a, there's b, exactly as it is on top, and we do the bitwise addition. So 1 plus 1 gives us 0, carry 1. 1 plus 1 plus 1 gives us 1, carry 1. 1 plus 1 plus 0 gives us 0, carry 1. 1 plus 1 plus 0 gives us 0, carry 1, and so it goes on 0, carry 1, 0, carry 1, 0, carry 1, and 1 plus 0 gives us 1. So this is our answer. Our final answer or result is supposed to correspond with 130. But look what happens now. This thing, as we know, is in 2's complement, this entire number. And this indicates to us that it is a negative number. And if we now go and do a 2's complement on this to get the decimal value, we actually get an answer of minus 126. Now we know 127 plus 3 is supposed to be 130, not minus 126. And this simply happens because there is an overflow happening in this particular case here. We know that the ranges for an 8-bit number that's in 2's complement, the ranges can only be between minus 128 and positive 127. And because we have positive 130, these 8 bits in 2's complement format is not enough to store this value in. We will need more bits. And that's the reason why we get this overflow over here. So, again, just to take note of this, when we do arithmetic operations on numbers in a computer, in 2's complement format in this example here, we should remember that each number and the result should be in the range defined by the bit allocation. So if we know the result's going to be smaller than minus 128 or larger than positive 127, in this case, in this examples that we used here, we cannot use 8 bits. We will have to go to the next bit level, which is 16 bits, and then we can store much larger numbers in there. Alright, so that's the end of this lecture. I will discuss this lecture with you on Monday, 11 May during the class, Monday morning, 8:30.